Hello guys, welcome back. We're still in lesson number 22 where we've been talking about optimization all the time, but why not throw in linear approximation as well? So this is actually a pretty straightforward, simplistic concept to do here. Really what this is that we're trying to estimate a value, some value of a on our function f of x. And we are going to use the equation of the tangent line or our derivative to actually tell us what that value is, but we're going to use a value that we actually already know. And so let me really quickly talk about the equation of how to get the linear approximation, and then once I do the example for you, it should make very much sense what I'm asking you guys to do here. But I want the equation of this tangent line, right? I want the equation of the tangent line. And that's going to give me this direct value of what's going on right here, at least with the rate of changes for this point. So if I want the equation of the tangent line, again, I'm using the point a comma f of a, and this function, this red function, is f of x. So my y value, I'm going to do y minus f of a, just like y minus y sub 1. Then the slope of this function, right, this rate of change is going to be f prime of x, but I want to evaluate it at a, right? I want to evaluate it at a. So this is going to be f prime of a, and then I'm going to do x minus a, right? Again, because the point, I need to erase this so you guys can see this. So the point that we're looking at is basically x comma y, but we're choosing some value a, and this is going to be our f of a. So this is the equation we have. If we were to simply move this over here, and I get y equals f of a plus f prime of a times x minus a, you get what you see right here. And this is the equation that you're going to use for linear approximation, or sometimes it's called linearization. So they're the same thing. So let's show you guys an example of what to do with this. Okay, so right up here at the top of the page, we do have the equation that we're going to use. And so the example says, given that f of x equals the square root of x, let x equal 4. Find the linearization, so that's what tells us to find the linearization of this function, and we want to approximate the square root of 4.05. Okay, so we want to know kind of the approximation for what this decimal value is. Well, like I said a couple minutes ago, is that we're going to use x equals 4 because 4 is really close to 4.05, and it's also a value that we know. We know the square root of 4 is equal to 2. So we're going to go ahead and write our equation out. And one of the things that just is a little bit weird about these problems that, I always tell students is that this right here, what we're trying to approximate, is going to be your x. Okay, I know the question says x equals 4, but based on this equation right here, just know that whatever we're trying to approximate, this is going to be the x. So x is going to be equal to 4.05. You know this because we have to easily find what f of a is. We don't know what f of 4.05 is. We're trying to approximate that, but we do know what this is. So I'm going to rewrite that as a. So a is 4. And again, right here it says it. So I don't want you guys to be confused about that particular part. Just remember that whatever we're trying to approximate is going to be the x. So x is going to be whatever we're trying to approximate, the value that we're trying to approximate. I cannot spell, I cannot write today, approximate. All right, so all we need to do is find these pieces. So f of 4 is going to be equal to the square root of 4, which is going to be equal to 2. Awesome. So this value is going to be 2. Well, I got to find f prime of a. Well, first of all, I got to find out what f prime of x is. Well, we all know that the derivative of the square root of x is just 1 over 2 square roots of x. So f prime of 4 is going to be equal to 1 over 2 times the square root of 4, which is going to be equal to 1 over 2 times 2, which is 1/4. So I have everything that I need to go ahead and plug in here, and we're solving for y right now. That's what we want. We want what y is. What is y? Y is going to be equal to 2, that's what f of a is, plus 1/4 times x, again, is 4.05, minus a. Okay, so we're going to start simplifying this down a little bit more. We're going to get y equals 2 plus, I'm going to go ahead and write this as 0.25. You'll see in a second why. And then 4 minus 0.05 is going to be 0.05. Now, we can do this mental math in our head. We may not like it, but we can do it. We have 25 times 5 is really what this is. So 25 times 5 is 125. But we have 2 decimal places here and 2 decimal places that we have here. So we have 4 decimal places that we have to deal with. So there's our 4 decimal places. So 0.0125. And then all we have to do is now just add them up, and we get our answer. So this says that our approximation, so the square root of 4.05 is approximately equal to this value right here. And that's all that you do. I went ahead and just put up the calculator here just so we see how good we were with our problem. So we do the square root and we do 4.05. We're going to move the calculator over, so we're good here, and we set the decimal answer, and then we get 2.01246, which again would go to 1.5. So we're really good with that. So that's what linear approximation is. And so very quickly, it's going to ask you about whether something is over or underestimate on this. So like if you look at this exact question that we just did right here, you know, over versus under for linear approximation. So you want to look actually at, you know, if I'm looking at a curve, and you look at the second derivative, So if I'm going to be concave down versus concave up, because remember, the linear approximation is going to be the tangent line at some values. So if I'm looking at these two examples here, my lines, if I'm concave down, right? So if I'm concave down, then I know this has to be over, right? This is going to be an overestimate. Because my second derivative, and this is all that you would have to do, is you'd have to find the sign of your second derivative and see what that value is. And then over here on the right-hand side, if I'm concave up, then I know that I'm going to be an underestimate because the lines are going to be under. And again, it's because your second derivative is actually going to be greater than 0. So if we look at our example up here, our first derivative was really going to be, and let's actually just for example do this because our function was the square root of x, right? So if I go ahead and look at this, and I say, okay, well, y equals the square root of x, where our derivative is going to be equal to 1/2 x to the negative 1/2. Let's not simplify that. Let's go ahead and find our second derivative. Well, our second derivative is going to be equal to negative 1/4 x to the negative 3/2. If I plug in 4, which is where we're evaluating, right? If I plug in 4, then we're going to get negative 1/4, which we're going to get a negative value. So we're going to get a negative value, which means since it's negative, then we have a concave down, right? So our value here, so y prime of 4 is less than 0, so we're concave down, which means that this is an overestimate. And I just showed you guys on the calculator that the actual value was 2.01246, and we approximated it at 0.5. So finding the second derivative tells us whether it's an over and under. And just remember, you can always graph it and think an over. Because remember, don't think that because the second derivative is negative that it's going to be an underestimate. Remember that negative means that it's going to be concave down. We're sad, concave down, so it's going to be an overestimate. So concave down is an overestimate, concave up is an underestimate. All right, so hopefully that makes sense, you guys, and I will see you in the next video.